Bismillahirrahmanirrahim. Assalamu alaikum students. Last time we were discussing applications of Gauss's law or theorem, and we discussed some applications. We continue with that topic with new applications. So this topic is continued. So I remind you, we already discussed electric field due to a point charge. This was our first application. Second was E due to an infinite line of charge, right? Third one was E due to an infinite sheet of charge, right? Here we proved that electric field due to a point charge is given by 1 by 4 pi epsilon naught q by r square, where symbols have their usual meaning. Here the expression was lambda by 2 pi epsilon naught r, and here the expression was sigma by 2 epsilon naught, right? Now we have fourth application. Now my fourth application of Gauss's law is a spherical shell of charge, right? Consider a spherical shell of charge. I showed that in cross section, right? So consider a spherical shell of charge. It will have some radius. Let capital R be its radius. So R is the radius of the shell, right? And this figure shows the cross section of that three-dimensional spherical shell of charge. R is the radius of the shell, and it will have some surface charge density. We represent that by sigma, right? So sigma is its surface charge density, and we assume sigma to be constant. So if sigma is constant, the spherical shell of charge is called uniformly dense spherical shell of charge, right? I have a spherical shell of charge. It has certain charge density. It has some total charge. So let Q be total charge. Q is total charge of the spherical shell. Sigma is surface charge density, and We assume that surface charge density is constant throughout. R is radius, right? Now there are two useful properties of this distribution of charge, and those two properties are called shell theorems. Two shell theorems. I will state them, then we will prove them using Gauss's law. So first shell theorem, or first property of this uniformly dense spherical shell of charge is like this. It says a uniform spherical shell of charge behaves for external points, behaves for external points as if all its charge were concentrated at its center. And second shell theorem, or second property of this distribution, is like this. It says a uniform spherical shell of charge exerts no electrostatic force on a charged particle placed inside the shell. Inside the shell. I repeat the statement. First theorem says a uniform spherical shell of charge behaves for external points as if all its charge were concentrated at the center. And the second one says a uniform spherical shell of charge exerts no electrostatic force on a charged particle placed inside the shell. I will first explain them, then we will prove these two results, these two theorems, shell theorems, using Gauss's law. Now, it is my uniformly dense spherical shell of charge. It has charge Q. Now, first shell theorem says if I select some point P outside the shell, which is R distance from the center of the shell, and if I place some charge at point P, let that be Q prime, then this will behave as if it's a point charge located in the center. That, in other words, means it will exert force on this Q prime charge as if all its charge were concentrated at the center. That means that will be given by 1 by 4 pi epsilon naught Q prime by R square. This is the meaning of this first shell theorem. That if I place any charge outside this shell, right, then the shell of charge will behave as if all its charge were concentrated at the center. That means the force exerted by the shell on the charge outside the shell will be same as if the shell is a point charge located at the center. That means it will be 1 by 4 pi epsilon naught charge of the shell, charge placed outside, and distance from the q prime charge to the center of the shell. So we are treating it as if the shell is a point charge located at the center. When force is this, that means, in other words, that electric field outside the shell will be same as the field due to a point charge located at the center of the shell having charge equal to that of the shell. That means electric field at point P will be 1 by 4 pi epsilon naught q by r square. This is the meaning of first shell theorem. The second shell theorem is easy. Second shell theorem says if you place a charge inside, that I named that q double prime, inside shell anywhere, the electrostatic force on the shell, on this charge q double prime will be 0. I write different color here. Q double prime will be 0. Actually, what happens? Uh, actually, when we say it exerts no electrostatic force, by that we mean it exerts no net electrostatic force on the charge placed inside the shell. What happens? Different pieces of the shell exert force on this, but they cancel out when we add them to find the net charge on to find the net force on the charge placed inside the shell. Got it? So I am saying second shell theorem says if you place some charge inside the shell, let that charge be q double prime, force on this will be 0. That is only possible when electric field inside the shell is 0. So we will prove these two results using Gauss's law. We'll first prove that electric field outside the shell is same as the electric field due to a point charge located at the center of the shell and having charge equal to total charge of the shell. And second shell theorem, we will prove that electric field inside the shell is 0. And remember, these two theorems are valid only when sigma is constant. So let us move to the proof. So proof. First A, that is first shell theorem. So I have this uniformly dense spherical shell of charge, right? It has certain radius r, it has certain charge q. Now we know sigma is the total charge density. Now consider a spherical Gaussian surface with radius r concentric with the shell, right? As shown in the figure, as shown in the figure 1. Let this be my figure 1. So I draw a Gaussian surface concentric with the distribution and with a r is the radius. So this is my spherical Gaussian surface. So it is concentric and it is enclosing the whole shell, right? It is enclosing the whole shell. Now since here we have spherical symmetry. So here we have spherical symmetry. That means if we are outside the shell at r distance from the center, at that distance in all directions, the distribution looks the same. Due to that, the electric field outside this positively charged shell will be only radial. That will have only a radial component. So if let me different color at one patch of the Gaussian surface, if this is dA vector, similarly will be directed E vector. And this will be true for any area patch of the Gaussian surface. Area vector and electric field will be outward, right? Because of the spherical symmetry. So applying Gauss's law, closed integral E dot dA is equal to Q by epsilon naught. Here Q is the charge inside the Gaussian surface. That is here Q also, because the Gaussian surface encloses the whole spherical shell which has charge Q. So Q is Q. This will become just EDA, because everywhere angle between electric field and area vector is 0, cos 0 is 1. E can be factored out because E is constant over the surface. Then I move here. This will be simply surface area of the Gaussian surface over epsilon naught. So E is 1 by 4 pi epsilon naught Q by r square. This proves my first shell theorem. I have proved that electric field outside is same as electric field due to a point charge located at the center of the shell having charge equal to the total charge of the distribution. But this is valid only when r is greater than r. That means when I'm outside the shell. So hence first shell theorem is proved, right? So we have proved first result, that it behaves for external points as if all its charge were concentrated at the center. Now proof for second B. It is simple. Again, consider this spherical shell of charge with radius r, where it has total charge q. Now consider a Gaussian spherical Gaussian surface. Spherical Gaussian surface concentric with the shell and lying inside it, right? So let this be my Gaussian surface, right? That R be its radius. This is my Gaussian surface, spherical Gaussian surface, concentric with the shell, and it is lying inside the shell. It contains no net charge. Applying Gauss's law, closed integral E dot dA is equal to Q by epsilon naught. There is no net charge inside the Gaussian surface, right? But Q is 0. Therefore, closed integral E dot dA is 0. Then you can use the spherical symmetry and see that it will become E closed integral dA is equal to 0. Then A is 0, right? So hence I have proved, but this is valid only when R is less than R. Previously R was greater than R. We were outside the shell. Now we are inside the shell. R is less than capital R. So electric field is 0. So if you place any charged particle inside the spherical shell, it will exert no force. This proves our second shell theorem. This proves the second shell theorem, right? Your homework problem. So your homework is question. The electric field components in figure 1, components in figure 1, I will give you the figure. Let me call it figure A, are E subscript X is B X raised power half, B X raised power half. EY is equal to EZ, both equal to 0, in which B is equal to 8830 Newton per coulomb meter raised power half. Calculate, change the color, calculate part A, the flux phi E, that is electric flux through the cube, and B is the charge within the cube, the charge within the cube. Assume that A is equal to 13 centimeter. I will give you the figure first. So my figure is like this. This is my X, this is my Y, this is my Z direction. Then I have cube. Just like this. Just like this. So this is my cube. This is A. This side is A. This side is A. This side is also A. And this distance of this face from the origin is also A. Distance of the face from the origin is also A. So this is my cube says face 1, face 2, face 3, face 4, right? Face 5 and face 6, right? So this is my figure A. I repeat the question. The electric field components in figure A are Ex varies with X and is given by Bx is per half, Ey and Ez are 0. That means electric field is parallel to the x-axis, right? P has value 8830 Newton per coulomb meter raised per half. And we have to calculate part A the electric flux through the cube and part B the charge within the cube. You have to assume that A, that is edge length of the cube, is 13 centimeter, right? This is all for today. Do your homework. Don't waste your time. Thank you. God bless you. Assalamu alaikum.